Drift with me now and imagine a world that feels both familiar and far away. It is the year 1977. The air on Earth hums with a quiet tension, a silent standoff between two great powers. But beneath the surface of that global unease, something else is stirring, something entirely different, a gentle and profound curiosity that whispers from the heart of humanity itself. This is a time of clunky technology and bold dreams, of rotary phones and the first flickering digital watches, a time when our television screens were still broadcast in grainy, black and white images of a man bounding across a dusty lunar landscape. We had reached the moon. We had stood on its surface and declared to the universe, we did it. But after that giant leap, a strange quiet settled in. The spotlight of public attention, which had so brightly illuminated the Apollo missions, began to dim. Budgets for space exploration were tightened. The collective breath we had held for so many years was finally released. And with that sigh, a question arose. What now? What's left? The answer was waiting. It had always been there, a silent constellation of giants spinning in the outer darkness, far beyond the familiar orbits of Mars and the asteroid belt. The gas giants, Jupiter, Saturn, Uranus, and Neptune. Worlds so vast, so distant, and so shrouded in mystery that for centuries they had remained little more than blurry points of light in our telescopes. Colossal, mysterious planets encircled by rings of ice, cloaked in swirls of gas, and orbited by dozens of strange, unknown moons. They were beautiful enigmas, untouchable and unseen. But in the quiet corners of NASA, among the engineers and the dreamers, a brilliant solution began to take shape. It wasn't about more power or bigger rockets, it was about patience. It was about a dance that the planets themselves were about to begin, a celestial ballet that happens only once every 175 years. In the late 1970s, those giants of the outer solar system would align in such a way that a single spacecraft, if launched at precisely the right time, could use their gravity to slingshot from one to the next, like a stone skipping across a pond. This was the Grand Tour, a breathtaking vision that in its original form was too expensive to pursue. But the dream didn't fade, it adapted. It distilled itself down to a more modest, yet still breathtaking plan. Instead of a fleet of probes, NASA would launch two twin spacecraft, identical in design, built with a simple elegance and a rugged stubbornness. They would be robust, smart, and designed for a journey that was audacious in its scope and poetic in its ambition. These were the Voyager missions. Imagine now a long, quiet room at the Jet Propulsion Laboratory. The air is still, but the minds within it are buzzing with a beautiful kind of noise, the hum of calculation and the murmur of curiosity. Pencils whisper across paper, drawing out trajectories. Scientists debate over the color of a planet's atmosphere. Engineers argue over the thermal shielding needed to survive a journey into the bone-deep cold of deep space. Every wire is a tiny strand of hope. Every piece of code is a whispered instruction. This mission isn't for the cameras or for the headlines. It is a slow, endearing act of faith. And what do you build for such a journey? You build something that must last, something that has no need of flashy screens or powerful microchips, something that is simple enough to survive for decades without a human hand to guide it. A single ship to carry a small, precious cargo, a collection of instruments, and a golden record. The golden record, perhaps the most poetic piece of the entire project. It wasn't a scientific instrument, it was a message. A greeting in dozens of languages, the sounds of Earth, from the laughter of children to the song of a whale. and a carefully selected mixtape of humanity's greatest music. It was a bottle cast into the cosmic ocean, a declaration that said, "We were here. This is who we are." The odds of it ever being found were impossibly small, but that wasn't the point. The point was the gesture itself, the simple, profound act of saying hello to the unknown. So, as we drift deeper into the silence of this story, let the image of that golden record, that tiny, shimmering time capsule, settle in your mind. It is a symbol of everything to come. It reminds us that at our core, we are not just a species of fear and conflict, but a species of curiosity and hope. A species that, even in a world full of noise, is capable of a very quiet and beautiful act, the act of reaching out. And with that thought, let us prepare for the beginning of our own journey, for the moment when two quiet ships, built in a long-gone era, stood poised to change the way we see everything. They were destined not to return, but to remind us what it truly means to leave. Chapter 2. The Architectures of Endurance. Visualize with me now the quiet hum of a clean room, a space so sterile that even the air feels different. It is here that the Voyagers are taking shape, not as sleek, futuristic starships, but as something more honest and resilient. They are built for the long haul, designed in an era when durability was a form of elegance, and a well-placed solder joint was a mark of artistry. The task was clear, but the challenges were immense. This was before the age of smartphones and cloud computing. The engineers at NASA's Jet Propulsion Laboratory worked with slide rules and punch cards, with pencils drawing careful lines on large sheets of paper. They were building something to survive not just a few years, but decades. Billions of miles from home, with no chance of repair, no pit stops, and no second chances. The first challenge was the environment itself. Space is a cold and hostile place. A vacuum filled with this silent thread of cosmic radiation and tiny, fast-moving particles of dust. Voyagers needed to be tough, not fast or flashy, just stubbornly, resiliently durable. The very skeleton of each spacecraft was a sturdy aluminum frame, designed to withstand the violent shudder of launch and the endless silent stress of a journey that would take them far beyond the sun's comforting warmth. From this central frame, the instruments and antennas extended like the delicate limbs of an insect. The most iconic of these was the great white high-gain dish, a graceful 3-meter-wide structure that looked like a satellite TV dish with a dream of the stars. This was to be Voyager's voice, and what a whisper it would be. Even now, more than 4 decades later, Voyager's signal, traveling across unimaginable distances, reaches us with a strength of less than a billionth of a watt. It is a whisper softer than the static buzz of an old television, yet the massive, listening ears of NASA's Deep Space Network can still hear it. Inside the spacecraft, the onboard computers were marvels of simplicity. Each Voyager carried a humble 69 kilobytes of memory. To put that in perspective, the smallest photo on your phone holds more data than Voyager's entire brain. There were no flashing lights, no touchscreens, just solid-state logic and pre-programmed instructions. These humble electronics were carefully designed to be radiation-hardened and utterly reliable. A command sent from Earth would take hours to reach the spacecraft, and another long, quiet journey for the response to return. It was a patient conversation conducted across the vastness of the cosmos. Power was another hurdle. Solar panels, the go-to solution for probes orbiting Earth, were useless out where the sun is little more than a brilliant star among other stars. The solution came in the form of radioisotope thermoelectric generators, or RTGs. These were like small, self-contained nuclear campfires. They used the heat from decaying plutonium-238 to create a steady stream of electricity, keeping the instruments warm and the lights on for decades to come. At launch, they provided enough power to run a few light bulbs. Today, that output has dwindled, but even in their old age, they still cling to life, a testament to their longevity. The scientific instruments themselves were a carefully curated collection, a small toolkit of sensors designed to peer into the unknown. Each spacecraft carried a magnetometer to measure the subtle magnetic fields of distant planets, plasma detectors to taste the solar wind, and cosmic ray sensors to feel the energetic particles from other stars. And of course, there were the cameras. Despite being less powerful than the one in your pocket, these cameras would go on to capture some of the most iconic images in the history of space exploration, from the swirling chaos of Jupiter to the elegant rings of Saturn. One of the most profound aspects of the design was its lack of a return ticket. Voyager wasn't built to land or to bring samples back or to be retrieved. It was built to simply keep going. This focus allowed the mission team to pour all their effort into quality and perfection. Every wire was checked and double-checked. Every piece of solder was precisely placed. They were building an artifact not just for a mission, but for a legacy. And so the Voyagers became more than just machines. They became time capsules, filled not just with technology, but with the quiet hope of the 1970s. They embodied our best selves, our curiosity, our ingenuity, and our enduring desire to reach out into the dark. Imagine now those twin ships standing silently on their launch pads, two small towers of human ingenuity, waiting for their moment. They have no voice of their own, only the quiet hum of their own systems and the patience of a world that is holding its breath. Chapter 3: The Great Escape. Drift with me now and visualize the final days of summer in 1977. The air is warm, the world is humming with disco music and the echoes of the moon landings. But on two separate launch pads in Florida, a more profound kind of sound is waiting to be born. The sound of two silent liftoffs, a quiet roar that would send two tiny ships on the longest journey in human history. These are the moments before the beginning. The twin spacecraft, Voyager 1 and Voyager 2, stood poised, identical in design, yet with slightly different destinies. You might think that Voyager 1 would launch first, being number 1. But as with so much in the cosmos, the journey did not follow a tidy numerical rule. Voyager 2, with its longer and more intricate path, lifted off first on August 20th, 1977. Just 16 days later, on September 5th, Voyager 1 followed, set on a faster, more direct trajectory to its initial targets. Their shared mission was extraordinary. It wasn't just about visiting one faraway world. It was about riding a cosmic highway, a planetary pinball game where each encounter would fling the spacecraft onward with even greater speed. This was made possible by the Grand Tour's celestial secret, a rare and beautiful planetary alignment that only happens once every 175 years. This gravitational ballet, known as a gravity assist, is one of the cleverest tricks in the spaceflight playbook. Imagine a small, graceful dancer approaching a spinning giant. As the dancer falls into the giant's embrace, they speed up. Instead of getting pulled into an endless waltz, the dancer elegantly slingshots around and is flung onward, faster and in a new direction. The giant doesn't even notice the stolen momentum, but for the tiny dancer, it makes all the difference. This wasn't just a fuel-saving maneuver. It was the key that unlocked the entire outer solar system. Voyager 2, with its more complex route, took a slower, more deliberate course, keeping its options open for a grander tour. Its destination was not just Jupiter and Saturn, but potentially Uranus and Neptune as well. It was the patient, hopeful sibling. Voyager 1, on the other hand, was all about speed and efficiency. Its path optimized for a swift passage to Jupiter and Saturn. After Saturn, its trajectory would take a sharp turn away from the plane of the solar system, soaring into the dark unknown above the planetary disk. The launches themselves were not the kind of grand spectacles that the Apollo missions had been. There were no crowds waving, no astronauts to be hailed as heroes, just a quiet, determined liftoff and a flurry of calculations. The Titan IIIe Centaur rockets, powerful and precise, pushed their precious cargo beyond Earth's gravity well and set them on a course that had been planned for years. The launches were textbook perfect, and within hours, both spacecraft were on their way, leaving Earth as a memory, a faint blue marble in their rearview mirror. As the Voyagers sped onward, a powerful feeling took hold. These machines, with their humble electronics and their stubbornly durable frames, were no longer just our creations. They were our emissaries, carrying not just instruments, but a golden heart filled with the best parts of us. They were writing a whisper of physics and a surge of human ingenuity into a cosmic ocean we had only ever dreamed of crossing. And so, the quiet beginning of one of humanity's greatest stories unfolded. Two small ships, built with the humble tools of the 1970s, were now hurtling through the dark, their journey just beginning, a testament to the idea that a single, fleeting planetary alignment, a dash of precision, and a whole lot of hope can take you to places you never thought possible. Chapter 4: The Great Red Eye. Drift with me now and imagine the long, quiet glide of a ship through the star-dusted night. After months of patient travel, the celestial highway began to show its first landmark. The whispers of the outer solar system grew louder, and a new kind of light, a cold, distant glow, began to fill the viewfinders. In early 1979, the silent form of Voyager 1 drew closer to its first destination, a world so large it could contain all the other planets in the solar system, with plenty of room to spare. This was Jupiter, the king of the planets. For centuries, we had admired its striped and stormy face through telescopes, a beautiful, enigmatic orb spinning in the dark. But now, as Voyager 1 and, a few months later, its twin, Voyager 2, approached, our view was about to be transformed forever. The first thing that struck the scientists was not the grandeur, but the sheer, breathtaking chaos. From a distance, Jupiter's banded atmosphere had looked serene, almost placid, but the close-up images from Voyager's cameras revealed a world in violent, magnificent motion. The calm bands gave way to a maelstrom of swirling storms, jet streams roaring in opposite directions, and ovals of gas the size of entire continents. And then, there it was, the Great Red Spot. This legendary storm, a feature first observed more than 3 centuries ago, was revealed in stunning textured detail. It wasn't just a red dot, it was a swirling crimson maelstrom, a hurricane so massive that it could swallow Earth whole and still have space left over. Voyager showed it to be a dynamic, living entity, its clouds swirling and twisting in a counterclockwise rotation with a speed that made terrestrial hurricanes seem like lazy whirlpools. The Great Red Spot wasn't alone. Dozens of smaller storms danced across the atmosphere, an intricate ballet of immense power and astonishing grace. The reason for all this drama lies in Jupiter's immense size and rapid spin. It is more than 11 times wider than Earth, and its day lasts less than 10 hours. This rapid rotation stretches its deep atmosphere of hydrogen and helium into the distinct bands we see and fuels the powerful storms that can rage for centuries. But the biggest surprises were not on the planet itself.
they were in the company it kept. Before Voyager, we knew of a handful of Jupiter's moons, but we assumed they were little more than cold, cratered rocks. What the spacecraft revealed was a planetary family bursting with character and secrets. First, there was Io, a moon that completely rewrote the rules of geology. Voyager 1's cameras captured something no one had ever expected: plumes of material shooting hundreds of miles into space. These were not gas or dust, they were massive volcanic eruptions. It was the first time an active volcano had ever been seen beyond Earth. Io was a chaotic mess of molten plains and sulfur lakes, a tormented landscape painted in wild yellows, reds, and oranges. The source of this violence? Tidal heating. Io is caught in a tidal tug-of-war between Jupiter and its neighboring moons, and the constant squeezing and flexing of its core generate enough heat to power relentless volcanism. Then came Europa. At first glance, it seemed calmer, a smooth, icy shell with very few craters. But Voyager's images revealed a surface crisscrossed with long, dark lines, like fractures in a frozen sheet of glass. These lines hinted at something far more profound: a liquid ocean hiding beneath miles of frozen crust. An ocean warmed by those same powerful tidal forces that held the tantalizing possibility of life. Before Voyager, Europa was just another satellite. Afterward, it became one of the most intriguing places in the entire solar system. The other moons, Ganymede and Callisto, also had their stories to tell. Ganymede was revealed to be the largest moon in the solar system, even bigger than the planet Mercury. Callisto, ancient and heavily cratered, wore its history on its face, a testament to billions of years of silent cosmic history. As the Voyagers flew on, they also studied Jupiter's immense magnetosphere, a region of space dominated by its magnetic field, which is 20,000 times stronger than Earth's. It's a vast, invisible shield that traps charged particles and creates intense radiation belts. Voyager had to be specially shielded just to survive its brief flyby. The spacecraft also caught sight of Jupiter's faint, dusty rings, a subtle discovery that proved Saturn was not the only ringed master in the solar system. By the time the encounters were over, Jupiter was no longer a distant gas ball. It was a complex, dynamic system of furious weather, intense radiation, and an entourage of moons that defied all expectation. The Voyagers had transformed a question mark into a living, breathing epic. The ships had already accomplished more than anyone had dared to hope, but this was just the beginning of their journey. With the chaos of Jupiter behind them, their next destination lay in the darkness ahead, a place of quiet, ethereal grace wrapped in shimmering rings of ice and starlight.
Chapter 5. The Master of Rings. Drift with me now, and let your mind settle on the quiet majesty of Saturn. If Jupiter was all fiery chaos, Saturn was its elegant, contemplative cousin. For centuries, its rings had captured human imagination, a beautiful, impossible piece of cosmic jewelry that seemed to defy the very laws of physics. Galileo saw them first in the early 1600s, though his telescope could only resolve them as ears on either side of the planet. Now, with the Voyagers approaching, we were about to get our first true, high-definition look at this iconic world. In November of 1980, Voyager 1 made its close approach, followed less than a year later by Voyager 2. The view was breathtaking. Saturn wasn't just a golden orb with rings, it was an intricate, living system. The planet itself, a stunning spectacle of shimmering golden bands and subtle storms, was dwarfed by the grandeur of its icy halo.
The rings were, of course, the stars of the show. We had long known them to be wide, but Voyager revealed their astonishing thinness. Made mostly of water ice, ranging from tiny grains to house-sized chunks, the rings stretch for more than 200,000 miles across, yet are often no more than 30 feet thick. That's like stretching a sheet of paper across the length of an entire football stadium. How they remain so perfectly flat and neatly arranged is a mystery that still fascinates scientists today. Voyager's cameras peered into that delicate lacework and revealed far more than a few broad bands. They showed thousands of individual ringlets with subtle waves, intricate gaps, and strange, puzzling patterns. The Cassini division, a dark gap visible even from Earth, wasn't empty at all. It was filled with its own set of thin, faint rings. Even more curious was the discovery of so-called shepherd moons, tiny satellites that orbit on the inner and outer edges of the rings. Their gravitational influence acts like a cosmic sheepdog, herding the particles and maintaining the sharp, elegant edges of the rings with invisible hands. The rings also showed ghostly features called spokes, which looked like radial lines drifting across the surface like shadows. Scientists aren't sure what causes them, perhaps magnetic interactions with Saturn's field, or brief clouds of particles kicked up by tiny impacts. Whatever their origin, they gave the rings a haunting, ethereal quality. The planet itself proved to be no less fascinating. While less colorful than Jupiter, its atmosphere was dynamic, with jet streams and storms. Voyager observed curious hexagonal patterns near the poles, though the full mystery of the strange polar hexagon would not be unraveled until decades later by the Cassini mission. And then there was Titan. Of all Saturn's many moons, Titan stood out. Larger than Mercury, it was shrouded in a thick orange haze. Voyager's instruments detected that this atmosphere was denser than Earth's and composed mostly of nitrogen. It was the only moon in the solar system with such a dense atmosphere. But the haze was impenetrable. Voyager couldn't see the surface, leaving scientists to wonder what lay beneath that mysterious veil. An icy, hydrocarbon-rich landscape? Lakes, or even oceans of liquid methane? The questions lingered, tantalizing and unanswered. Voyager 1's flyby of Titan was a pivotal moment for the mission. To get a good look at this intriguing moon, Voyager 1 had to take a path that sent it out of the plane of the solar system after the encounter, ending its grand tour of the planets. It was a deliberate choice, a trade-off that sacrificed a potential flyby of the distant ice giants for a closer look at this mysterious moon. Voyager 2, by contrast, skipped the close-up of Titan and stayed in the solar system's main lane, preserving its route to the outer planets. With its job at Saturn complete, Voyager 1 bowed out of the planetary tour and began its new, solitary journey into interstellar space, leaving Saturn to wave farewell with its shimmering rings. Its planetary tour was over, but its grander voyage had only just begun. It left behind an endless stream of data, stunning images, and a new understanding of a planet that had once been a distant enigma. Saturn, with its quiet grace, was now part of our story. Chapter 6: The Forgotten Siblings. Drift with me now and journey farther still into the deepest, coldest reaches of our solar system. Long after Voyager 1 turned its gaze outward toward the galaxy, its twin, Voyager 2, continued its quiet, patient glide. The year was 1986. Voyager 2 had already earned a glowing resume of close encounters with Jupiter and Saturn. But it wasn't finished. It was headed for the last two unexplored worlds in our planetary family, the ice giants, Uranus and Neptune. No other spacecraft had ever visited them, and to this day, no other has returned. Voyager 2 remains our sole emissary to these remote, enigmatic worlds. First up was Uranus. Voyager 2 arrived in January of 1986. At first, it looked almost too simple. A pale turquoise orb, seemingly featureless and calm. But as the spacecraft's instruments began to work, they peeled back the stillness to find a bizarre complexity lurking beneath the calm. The most striking feature of Uranus is its peculiar tilt. While most planets spin like tops, upright and steady, Uranus spins on its side, rolling around the Sun with an axial tilt of nearly 98 degrees. No one knows for certain how it ended up that way, but the result is a world of extreme seasons. One pole can face the Sun for over 20 years, bathed in constant light, while the other is plunged into a decades-long darkness. The atmosphere itself was colder than anything previously measured, a frigid minus 370 degrees Fahrenheit. Voyager detected faint cloud bands and signs of wind, but nothing as dramatic as Jupiter's storms. The planet's apparent stillness, however, was deceiving. Later analysis of the data would show that Uranus has winds of up to 500 miles per hour, hidden beneath its thick, tranquil haze of methane and ammonia. The magnetic field was an even bigger surprise. Unlike Earth, which has a magnetic field neatly aligned with its rotation, Uranus is tilted by nearly 60 degrees and offset from the planet's center. This creates a wobbly, lopsided magnetosphere that twists and shifts with each rotation, a delightful curveball that forced scientists to rethink how planetary magnetic fields are formed. Voyager 2 also discovered 10 new moons and a faint system of dark, narrow rings. These rings, unlike Saturn's shimmering halo, were almost invisible, made of rock and dust coated in dark material that reflected very little sunlight. The spacecraft also captured an unforgettable view of one of the moons, Miranda, a small, battered orb that looked like it had been shattered and reassembled from spare parts, with enormous cliffs and strange, scarred valleys. After the Uranus flyby, Voyager 2 continued its long, solitary journey. It was a testament to both its durability and the mission's quiet ambition. It traveled another 1 billion miles, all while hurtling through the dark with a failing power supply and a dwindling suite of instruments. It was a journey of pure endurance. Then, in August of 1989, Voyager 2 reached its final planetary target, Neptune. The eighth and final planet in our classical solar system, Neptune appeared as a deep blue jewel in the viewfinder. But unlike Uranus, Neptune was not shy. It was dynamic, vibrant, and full of surprises. Despite being even farther from the Sun, Neptune was remarkably active. Voyager 2 discovered massive storm systems, including the famous Great Dark Spot, a swirling oval roughly the size of Earth. Winds on Neptune reached supersonic speeds of up to 1,300 miles per hour, the fastest observed in the entire solar system. How this cold, distant world generates such powerful weather remains a profound mystery. Like Uranus, Neptune's magnetic field was strange, tilted and offset, giving rise to a magnetosphere that writhed and wobbled with each rotation, a delightful curveball that forced scientists to rethink how planetary magnetic fields are formed. Then came Triton, Neptune's largest moon. Voyager 2 found it to be a cold, strange, and unexpectedly active world. The spacecraft saw geysers of nitrogen gas erupting from its surface, a sign of what is known as cryovolcanism. This activity hinted at internal heat, perhaps driven by radioactive decay or tidal forces. Triton's retrograde orbit, meaning it orbits in the opposite direction of Neptune's rotation, was a strong clue that it was likely a captured object, perhaps a wanderer from the outer reaches of the solar system. The Neptune flyby marked the end of Voyager 2's planetary tour. After that, its cameras were turned off for good. But what it left behind was remarkable. It had transformed distant blue dots into real, complex worlds, moons with geysers, storms faster than sound, and magnetic fields that danced like drunken tops. Voyager 2 didn't just extend the mission, it redefined what was possible. It proved that the most remote places can hold the richest stories if we are willing to go far enough to hear them. The great planetary tour was over, but the Voyagers were just beginning their longest and most solitary journey of all.
Chapter 7. The Cosmic Mixtape. Drift with me now, and let's leave the planets behind. We're moving into the quiet, interstellar night, where the sun is just another star, and the background hum of the universe grows louder. It's a place no human has ever been, yet a piece of us is already there. It's the golden record, humanity's first and only mixtape for the cosmos. Imagine a bottle cast into a vast, dark ocean. It might never be found. It might drift for an eternity. But the act of sending it, the sheer audacious hope in that single gesture, that's the point. The golden record was the brainchild of a small, imaginative team led by the astronomer Carl Sagan. The Voyager missions were already ambitious enough, but Sagan and his colleagues saw an opportunity to add something more, something profoundly human. If the spacecraft were going to leave the solar system entirely, they reasoned, why not attach a message, a greeting in case an alien civilization ever found it in the far future? The odds of this were microscopic. Voyager is a tiny ship in an impossibly vast galaxy, but the gesture was everything. The result was a 12-inch gold-plated copper disc, a true phonograph record, encased in a protective aluminum jacket. It was a time capsule, an art project, and an interstellar ambassador all rolled into one. And it had to represent, in just over an hour, the entire essence of life on Earth. No pressure. The team worked quickly, with a deep sense of wonder. They weren't just scientists, they were curators of the human experience. They started with greetings. The record holds spoken messages in 55 languages, ranging from ancient Sumerian to modern Mandarin. Some are formal, others are warm and playful. The greeting in English is simple and sweet. Hello from the children of planet Earth. It's delivered in the clear, hopeful voice of a child, a sound that is both a hello and a promise. But the team didn't stop with language. They included a rich tapestry of natural sounds from our planet. These were not just academic choices. They were designed to be emotional. The record contains the roar of surf, the rustle of wind, the crackle of thunder. It holds the calls of birds, the laughter of children, the sound of a kiss, and even the whoosh of a rocket lifting off. One particularly haunting addition is the song of a humpback whale, an eerie and beautiful echo cast into the cosmic silence. Then came the music. The record holds 90 minutes of carefully selected music from around the world, intended to showcase our diversity and our unity. There is a Bach Brandenburg concerto, a gamelan piece from Indonesia, a Navajo night chant, and the melancholy blues of Louis Armstrong. There is also a track from Blind Willie Johnson, Dark Was the Night, Cold Was the Ground, a blues recording filled with wordless moans. Carl Sagan described it as expressing the human condition better than any spoken language could. The record also contained 116 images, encoded in analog format. These images were a kind of visual poem designed to introduce whoever found the record to our planet and our species. There were pictures of landscapes, animals, human anatomy, people eating and dancing, a mother nursing her child, and a photo of Earth from space. There were also scientific and mathematical diagrams, pulsar maps, and the structure of our DNA, all designed to give the finders a frame of reference. One of the most poetic and personal inclusions was a set of brainwaves from Anne Druin, a member of the production team who later became Carl Sagan's wife. For an hour, electrodes recorded her neural activity as she meditated on a wide range of ideas, including the history of Earth, the nature of humanity, and the experience of falling in love. That brainwave data was then encoded into the record, a mental fingerprint frozen in time. Somewhere in deep space, Anne's thoughts continue to travel, a heartbeat of human consciousness reaching into the dark. It's easy to dismiss this project as a romantic gesture, and in many ways, it was. But it was also a deeply practical statement. It reminded us that space exploration isn't just about rocks, orbits, and radiation belts. It's also about meaning, about sending not just our machines, but something of ourselves into the cosmos. Carl Sagan once said that the record was a bottle cast into the cosmic ocean. It might never be found, and if it is, it might not be understood. But the act of sending it, the sheer audacious hope in that single gesture, that's the point. The Golden Record was the brainchild of a small, imaginative team that continues to pierce the interstellar night. It's comforting in a strange way to know that somewhere, billions of miles from here, our little golden disk is still flying. It's not broadcasting, it's not blinking or beeping, it's simply there, turning slowly, gently, forever. A quiet promise that we were here, that we made music, that we looked up and wondered, and that we said hello. The 2 copies of the Golden Record, one on each spacecraft, are now the most distant human-made objects in existence. They carry our story into a silence no human has ever known, a final, beautiful gesture of hope and curiosity. Chapter 8. The Pale Blue Dot. Now turn your mind's eye away from the darkness ahead. Look back with me, not with longing, but with a sense of quiet perspective. By the year 1990, Voyager 1 had completed its grand planetary tour. It had flown past Jupiter and Saturn, snapped its stunning photos, and helped rewrite the textbooks. Now it was a silent pilgrim, drifting into the deep, beyond the orbits of the known planets. Most spacecraft, once their primary mission is complete, simply fade from public view. But Voyager wasn't done yet, not because it had more science to perform, but because it still had one more picture to take. A picture not of a planet or a moon, but of us. The idea was simple in concept, but profound in spirit. Turn Voyager's cameras back toward Earth and take a final snapshot from the edge of the solar system, a family portrait of sorts, with the sun and its planets seen from billions of miles away. It was Carl Sagan, ever the poetic voice of cosmic perspective, who pushed hardest for the idea. He believed that such a photograph could offer a rare and powerful moment of reflection, a visual reminder of our small place in the universe. There was some resistance to the plan. Engineers were cautious. Voyager's cameras were not designed to point near the sun, even from that great distance. A misstep could have damaged sensitive equipment, but by 1990, the risk was minimal. The cameras were already being retired from regular use, and the opportunity was too rare to pass up. So on February 14th of that year, Valentine's Day, NASA sent the command. The spacecraft, a tiny pinprick of human ingenuity, slowly rotated in the silent blackness. The shutter clicked. And the result, at first glance, was not particularly dramatic. In the final image, Earth appeared as a tiny pale blue dot, less than a pixel wide. It was caught in a shaft of scattered sunlight, a faint shimmer against the immense darkness of space, almost lost in the static. If you didn't know what you were looking at, you might have missed it entirely. But when you understood what you were seeing, it became one of the most profound photographs ever taken. That faint speck was Earth, home. Everyone you've ever known, every civilization, every story, every joy and every sorrow, all contained within a single shimmering mote of light. From nearly 4 billion miles away, our planet was reduced to a whisper. Carl Sagan later reflected on this image in what became one of the most moving passages in the history of science communication. In his book, Pale Blue Dot, he wrote, "Look again at that dot. That's here. That's home. That's us." Then he expanded on what that dot contained. Every king and every peasant, every hopeful child, every hero and coward, every corrupt politician, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. Carl Sagan's words were not just poetic, they were a gentle plea. He reminded us of the folly of human arrogance, of the endless battles we fight over borders and ideologies, and of the importance of kindness and of preserving our fragile planet. From a cosmic perspective, we're all riding the same speck of dust through an indifferent universe. That photograph, taken from the edge of the known solar system, became a mirror held up to humanity. It didn't show us our grandeur, but our fragility. And interestingly, Earth wasn't the only object captured in that portrait. Voyager's cameras also snapped images of Neptune, Uranus, Saturn, Jupiter, and Venus, all arranged together as a family portrait. But Earth, that pale blue dot, stole the show. The subtle blue tint in the image comes from the scattering of light by our atmosphere, the same phenomenon that makes the sky blue when we look up. Even from billions of miles away, that soft blue is visible. It is the color of oceans and sky, of breathable air and liquid water, a subtle clue that this tiny speck is unique and special. The image also captures the profound loneliness of space. There are no other lights, no flags, no flares, just a pinprick in a vast black sea. But that emptiness, far from being depressing, is actually kind of freeing. It strips away the noise and reminds us of what truly matters, not territory or titles, but connection, curiosity, and the desire to understand our world and our place in it. After this final farewell portrait, Voyager's cameras were powered off for good. It would never take another photograph. In that way, the pale blue dot was Voyager's final artistic statement, a last look back, a gentle turning of the gaze before heading into the long silence of interstellar space. And with that, it gave humanity a gift that no other mission had offered: perspective. A reminder that even in the vastness of space, a tiny world can hold infinite meaning, and that maybe, just maybe, looking back from a great distance helps us see what is right in front of us a little more clearly. Chapter 9. Beyond the Sun's Breath. Drift with me now and imagine a house where the warmth from the fireplace, the sun, slowly fades. We live comfortably in its light, but far beyond the familiar rooms, the house has a boundary, a point where the warmth ends and the wild, endless cold begins. For the Voyager spacecraft, that boundary is something called the heliopause, and crossing it marked one of the most significant milestones in the history of human exploration. To understand this journey, we have to see the sun not just as a source of light, but as a cosmic campfire, sending out a constant stream of charged particles known as the solar wind. This solar wind blows outward in all directions, creating a vast magnetic bubble around our solar system. That bubble is the heliosphere. Inside it, the sun's influence reigns supreme. Its magnetic field shapes the environment, and its particles fill the void. But eventually, that influence has to end. The solar wind weakens as it pushes against the material between the stars, a cold, sparse mixture of gas and dust known as the interstellar medium. The heliopause is the boundary where the pressure from the solar wind finally gives way to the pressure of the interstellar medium. It is the outer skin of the sun's protective bubble. Beyond that, the long, silent journey through the galaxy truly begins. Scientists had long predicted where this boundary might be, but no one had ever visited it. Not until Voyager. In August of 2012, after more than 35 years of travel, an extraordinary announcement was made. Voyager 1 had crossed the heliopause. It was the first human-made object to enter interstellar space. It had officially left the sun's domain. But how do you know you've crossed an invisible, shifting boundary? There's no glowing sign that says, "You are now leaving the solar system." Voyager's instruments had to feel the change in its environment. The first clue was a drop in solar particles and a simultaneous sharp increase in cosmic rays, the high-energy particles streaming in from outside the solar system. That was a major red flag, a signal that Voyager was tasting a new kind of space. Then came the definitive moment, a solar shock wave. An energetic burst of particles from a distant solar flare reached Voyager more than a year after it left the sun. As that wave hit the spacecraft, its plasma detectors recorded a sudden, dramatic jump in the density of the space around it. The plasma density had increased by a factor of 40, a striking confirmation that Voyager was now in the much denser interstellar medium. That sealed it. The spacecraft had truly crossed the threshold. It's important to note that while Voyager 1 is in interstellar space, it hasn't left the solar system entirely. The sun's gravitational pull extends far beyond the heliopause, deep into a theoretical shell of icy bodies known as the Oort cloud. Voyager, moving at over 38,000 miles per hour, won't reach the inner edge of the Oort cloud for another 300 years and won't exit it for another 30,000. So technically, it's still within the sun's gravitational neighborhood, but it is beyond the sun's direct protective influence. In November of 2018, Voyager 2 followed its sibling into interstellar space, though it took a different route. For the first time, we had not one but two data points from the edge of the sun's domain, providing valuable and often surprising information about the nature of the interstellar medium. Voyager found that the space out there is colder, denser, and more complex than previously imagined. It hums with low-frequency waves and is shaped by magnetic forces that reach across light years. Crossing the heliopause was a symbolic boundary as much as a scientific one. Voyager had gone from being a planetary mission to a galactic one. It had become an interstellar traveler. This was the fulfillment of a dream going back centuries, the idea of traveling to the stars. Voyager 1 is the first to actually do it, not with speed or glamour, but with quiet, faithful endurance. And it's still talking to us, faintly, patiently, a signal so weak that it takes over 22 hours to reach Earth. But it comes through, a whisper from beyond the sun, telling us about magnetic fields and particle density and the subtle nature of the interstellar breeze. Crossing the heliopause didn't make front-page news for long, but it was one of the most important thresholds humanity has ever crossed.
it marked the beginning of a new chapter for how we see ourselves. Voyager left the warmth of the solar bubble and entered the cold, quiet dark, and it kept going. That perseverance, that curiosity, that quiet push beyond every horizon, it's hard not to see it as a reflection of something deeply human. A part of us left the solar system, and it hasn't looked back.
Chapter 10. The Long Goodbye. Drift with me now and listen for a whisper in the cosmic dark. After more than 4 decades of continuous flight, the Voyager spacecraft are still going. They no longer snap dramatic photos or soar past new worlds. And yet, even now, these twin explorers continue their long, lonely journey outward, slipping farther into the great unknown, while their faint voices still reach us across the cosmic silence. Voyager 1, the faster and farther of the two, is currently more than 15 billion miles from Earth. To put that distance in perspective, light itself, the fastest thing in the universe, takes over 22 hours to travel from Voyager 1 back to us. It is the most distant human-made object in existence. Voyager 2 is a little behind, traveling in a different direction at a slightly slower speed, but not by much. It is now more than 12 billion miles from Earth. At these incredible distances, nothing is easy. Communicating with either spacecraft is a delicate dance of timing, calibration, and hope. NASA's Deep Space Network, a global array of enormous radio antennas, listens day and night for Voyager's faint signal. And faint is an understatement. By the time their transmissions reach Earth, they are a whisper, about 10 billion times weaker than the power needed to operate a digital wristwatch. Detecting them is like picking up the gentle ping of a cell phone from another planet. And yet, the whispers arrive, faint but steady, patiently spelling out data that helps scientists learn about the space beyond our solar bubble. But these spacecraft are getting old and tired. Each Voyager was designed to operate for about 5 years. 5 years, that was the plan. Just enough time to make it to Jupiter and Saturn, send back some photos, and retire with honor. Instead, they have kept going for nearly 50 years, far beyond their original expectations. Of course, they have had to make sacrifices to stay functional. Their power sources, the RTGs, are slowly but surely fading. At launch, they generated around 470 watts of power. Today, they produce less than half of that, and the power output is still falling. Less power means fewer systems can remain on. Over the years, mission controllers have had to make tough choices, like managing a dimming lantern on a cold night. They've shut down heaters, turned off backup systems, and selectively powered down scientific instruments. Each decision is a small, quiet moment of mourning. An instrument isn't broken, it's just out of energy. As of now, each spacecraft has only a handful of instruments still running. The cameras were turned off decades ago to conserve energy and bandwidth, but they can still measure things, magnetic fields, charged particles, and plasma waves, and that data is invaluable. Voyager is the only mission giving us direct measurements from the interstellar medium, a region we have never visited before. The environment out there is very different from the sunlit regions we know. There are no planets, no rings, no moons, just vast emptiness, punctuated by cosmic rays and drifting atoms. Voyager is helping us understand how our sun interacts with the rest of the galaxy, and how the edge of the solar system blends into everything beyond. The spacecraft themselves, built in the era of disco and floppy disks, remain surprisingly healthy. Their main computers are still functioning. The same redundant programming systems that once aimed cameras at Jupiter's moons are now carefully regulating their thermal balance and signal timing. Occasionally, a glitch occurs, a command gets garbled, a system hiccups. But engineers at NASA's Deep Space Network, many of whom weren't even born when Voyager launched, know how to coax the spacecraft back into line. In 2023, for example, Voyager 1 began sending back corrupted data. Months of patient detective work eventually led to a solution.
Engineers deduced that a single faulty memory chip had likely gone bad. They crafted a workaround, a kind of cosmic software patch, and beamed it across the stars. It took over a day for the signal to arrive and another day to confirm success. And it worked. Each fix is a minor miracle. Each transmission is a small triumph. Of course, the end is inevitable. At some point in the next few years, the remaining instruments will be shut off one by one. The power will dwindle to the point where even the radio transmitter can no longer function. When that happens, the signal will fade and Voyager will go silent. Not because it failed, but because it succeeded for far longer than anyone thought possible. And yet, the spacecraft won't stop. They will keep traveling, a silent, graceful drift. Long after they fall silent, long after Earth loses contact, Voyager 1 and Voyager 2 will continue their journey. In about 40,000 years, Voyager 1 will pass within a light year or two of a small star called Gliese 455. By then, Earth's continents have shifted, languages have changed, and Voyager's signal will have long been a memory. But the spacecraft will still be out there, intact, drifting between stars. A tiny piece of human craftsmanship sailing through an unimaginable sea.
Chapter 11, The Message in a Bottle. Drift with me now and imagine a profound silence. Out there, in the chill of interstellar space, two small spacecraft are coasting, their last sparks of power fading away. But if you were to lean in close, very close, you might just hear the whisper of something else. The quiet song of the golden record, a final message in a bottle cast into the cosmic sea. It is easy to imagine the end of the Voyagers in terms of technology, systems failing, power dwindling, a final heart-wrenching loss of signal. But the Voyagers are not just machines. They are carrying a legacy, a piece of us that will continue to exist long after their final transmission fades. That legacy is the golden record, and it was never about high odds or a guaranteed reply. Carl Sagan and his team knew the likelihood of any civilization ever finding this tiny artifact was vanishingly small. The galaxy is an impossibly vast place, and the distances between stars are almost beyond comprehension. But as a thought experiment and as an act of pure, audacious hope, the idea is irresistible. So let's suppose that thousands or even millions of years from now, an alien civilization, intelligent and curious, intercepts one of the Voyager spacecraft. It would be an object of great curiosity, a cold, silent artifact, no larger than a compact car, glinting faintly in the starlight. But what would truly capture their attention is that strange golden disk bolted to the side and encased in a protective aluminum jacket. It would be the extraterrestrial equivalent of finding a message in a bottle, except the bottle is made of metal and the ocean is about 98% empty. Imagine their scientists in a lab cautiously unbolting the disk and discovering the engraved diagrams on the cover. These are the instructions for playback, etched in a symbolic language of mathematics and physics, showing how to assemble the needle and how to decode its contents. It might be the interstellar equivalent of assembling a piece of furniture without a manual, but it would be fascinating. The diagrams include universal signposts, the hydrogen atom, mathematical constants, and a map of pulsars to show the location of Earth. With time and effort, they might figure out how to play the record and reconstruct the encoded images and sounds. And then the real adventure would begin. What would an alien make of Chuck Berry's Johnny B. Good, a rollicking, joyful slice of 1950s rock and roll? To us, it is iconic. To a species with no ears, no cultural context, and perhaps no concept of rhythm, it might come across as pure emotional chaos, or a distress signal. The musical selections were deliberately diverse, a carefully curated mixtape of Earth's sounds.
There is Bach, Beethoven, and Louis Armstrong, but there is also traditional music from Indonesia, Senegal, Bulgaria, and Peru. If nothing else, the finders would be able to tell that Earth was a noisy, diverse place, capable of creating art and expressing emotion. And then there are the sounds, a sonic collage of our world. The roar of the ocean, the cry of a baby, the sound of a kiss, the hum of a rocket lifting off. One can only imagine the conversations among alien analysts trying to decode what any of this means. What is the sound of the wet smacking? A ritual? An emotional bonding? The song of the humpback whale? Surely a profound philosopher. There is something both humbling and hilarious about the idea that a highly advanced civilization might one day sift through our audio leftovers and try to reconstruct what kind of beings we were. The record also holds images, 116 of them, showing landscapes, animals, anatomical diagrams, and people eating, dancing, and giving birth, all very ordinary to us, but to someone without context, it might look like documentary footage of a bizarre carbon-based civilization that once flourished on a moist blue marble. And then there is the most personal inclusion, the brainwave data of Anne Druin, a moment of beauty frozen in electromagnetic patterns. To us, it represents the experience of falling in love and contemplating the history of our world. To them, it might be a series of erratic pulses. But who knows? Maybe they will be able to decode not just the signal, but the feeling behind it. Of course, all of this assumes the finders are capable and interested. Maybe they'll glance at the record, shrug their appendages, and go back to harnessing dark energy. But maybe, just maybe, they will listen. And in that listening, they will hear the laughter of children and the songs of whales. They will hear ancient greetings and a spinning record, the whisper of wind and the hum of machines. They will hear Earth, not as a collection of data, but as a living, striving, singing planet that once looked up at the stars and wondered, are we alone? In that sense, the message isn't just for aliens, it's for us. It's a declaration frozen in gold that says, this is who we were. We tried to understand. We tried to reach out. We made something beautiful, and we sent it into the dark. And even if no one ever finds it, even if the record spins through space untouched for 1 billion years, it still matters because it's out there, still drifting, still whispering, still hopeful. A testament to the idea that sometimes the simple act of sending a greeting is a story in itself.
Chapter 12. The Enduring Legacy. Drift with me now and reflect on the long, quiet echoes of a mission that began in a different time. It's hard to imagine a space journey that has lasted longer, traveled farther, or touched more hearts than Voyager. Launched in the late 1970s with the tools of an earlier age, these twin spacecraft weren't just explorers. They were ambassadors, archivists, and accidental poets. And while they continue to coast silently through interstellar space, their influence echoes loudly here on Earth. Voyager's legacy didn't end with its last planetary flyby. If anything, that's when its true impact began. It lit a spark, not just among scientists, but in the imagination of an entire planet. It's hard to imagine a space journey that has lasted longer, traveled farther, or touched more hearts than Voyager. Launched in the late 1970s with the tools of an earlier age, these twin spacecraft weren't just explorers. They were ambassadors, archivists, and accidental poets. And while they continue to coast silently through interstellar space, their influence echoes loudly here on Earth. Voyager's legacy didn't end with its last planetary flyby. If anything, that's when its true impact began. It lit a spark, not just among scientists, but in the imagination of an entire planet. It's no exaggeration to say that Voyager changed how we think about space exploration and left footprints on the path that many future missions would follow. For planetary scientists, Voyager was a revelation. Before it, the outer solar system was a blur of fuzzy, telescopic images and educated guesses. Voyager turned those question marks into high-resolution answers. Moons, once assumed to be lifeless and inert, were revealed to be geologically active. Worlds once thought to be simple gas balls were found to have complex weather systems and exotic magnetic fields. All of this redefined what we considered interesting in the solar system. Suddenly, moons were in the running for potential habitats for life. Atmospheres were more exotic, planetary weather more extreme. There was more to see, more to wonder about, and much more to explore. And explore we did. Missions like Galileo at Jupiter, Cassini at Saturn, and Juno at Jupiter didn't just follow in Voyager's footsteps, they stood on its shoulders. They were designed to provide the long, slow answers to the questions Voyager first asked. Cassini, for instance, a mission that orbited Saturn for over a decade, was a direct heir to Voyager. It didn't just look at Titan's atmosphere, it dropped a lander into it. It didn't just admire Saturn's rings, it mapped their structure in exquisite detail. These newer missions took the treasures Voyager had cracked open and sifted through them with tweezers and microscopes. Even missions to other targets, like New Horizons at Pluto, drew on Voyager's legacy, earning the nickname Voyager 3 because its spirit was the same: a single-shot flyby, an encounter with a world we'd never seen up close, a moment of pure awe. Voyager also set new standards for what long-duration missions could look like. It showed that with good engineering and a bit of luck, a spacecraft could remain operational not for months, but for decades. That changed how agencies thought about planning, funding, and maintaining missions. It also changed how scientists thought about their own careers. A student just starting out in the 1980s could work on Voyager their entire life, and some did. But Voyager's legacy isn't confined to labs or launch pads. It also punched its way into pop culture. It showed up in films and was referenced in countless documentaries, books, and songs. It became a metaphor for persistence, for exploration, for humanity's quiet courage to look outward. The Golden Record in particular became a cultural icon, celebrated and parodied, and used as a seed for countless stories. More than anything, Voyager became a symbol, not just of triumph, but of wonder. It didn't explode across the sky like Apollo, or land like a dusty hero like the Mars rovers. It just kept going. A tiny whisper in the dark, a vote of confidence in the long view. The spacecraft themselves, simple as they seem now, were engineering marvels. Built with 1970s technology, hand-soldered circuits and analog tape recorders, and computers with less memory than a modern calculator. They've outlived most of the people who designed them. Their very endurance has become legendary. And yet, they are still making discoveries, still sending back data from regions no other spacecraft has ever traveled. Voyager also reshaped our philosophical understanding of exploration. It wasn't just about reaching new places, it was about asking better questions. What is the shape of a planetary magnetic field? How does solar wind interact with interstellar space? These were once the domain of theory. Now, thanks to Voyager, we have data. Even the way we talk about Voyager has changed. It is no longer just a probe. It has become a kind of cosmic poet, carrying humanity's dreams across the stars. Not loudly, not boastfully, but persistently, patiently, with the same quiet strength that marks our best stories. Perhaps that is the real legacy of Voyager. Not just what it discovered or where it went,
but what it reminded us about ourselves. That we are a species that asks questions, that we build things not just to use, but to understand, and that we sometimes make art, not for fame or profit, but because it feels right to send music to the stars. Voyager's journey has been a slow unfolding, a message in a bottle not meant to be answered, but simply to be cast into the sea because sending it said something meaningful about the ones who did. As long as the Voyagers are still drifting, still sending, still spinning their golden records through the dark, a piece of us is out there, not searching for recognition, but quietly carrying the legacy of wonder.
Chapter 13. The Stars in Our Hands. Drift with me now, and close your eyes. Imagine the vast, cold emptiness of space beyond the planets and the cold breath of the heliosphere, a place where the sun is just another bright dot, and the background hum of the universe grows louder. It's in this profound and beautiful silence that our story finds its quiet conclusion, but not its end. Voyager 1 and Voyager 2 are still out there, still traveling, still listening. They are old now by any standard. They were born in a world of rotary phones and disco balls, handwritten code and slide rules. They launched when some people were still convinced that Pluto was the final stop on our cosmic tour. They've flown through solar flares, radiation belts, and the ever-thinning edge of the sun's influence. They've seen worlds we once only guessed at, and sent back evidence of geysers, volcanoes, rings, oceans, and storms. And now, with just a few instruments still warm, they continue into the vast silence. But it isn't really silence they move through. It's just too quiet for our ears to notice. The space beyond the solar system hums with charged particles and ripples of ancient starlight. It's a place where atoms drift for eons without meeting, where distance loses all practical meaning, and where time itself stretches out like a road without signs. And yet, in the middle of all that quiet, something human is there. A piece of us wrapped in metal and gold, humming softly with fading power and carrying a message we wrote long ago. It's easy to forget how extraordinary that is. We built these spacecraft to explore the outer planets. That was their job, their assignment, their scope. But the moment they passed those final planetary encounters, they became something more. Not because they changed, but because we did. We realized they were no longer just tools. They were storytellers, pilgrims, time capsules, cosmic postcards with no return address. Voyager's journey is in many ways a metaphor for what it means to be human, to ask questions that have no clear answers, to build things that will outlive us, to wonder not for profit or conquest, but for curiosity, for the sheer joy of seeing what's out there. The spacecraft aren't fast, they're not flashy, they're not built to impress, but they persist, and there's a quiet dignity in that. Even now, long after their cameras have gone dark and most of their instruments have been turned off, they still speak. Their signals are faint, weaker than a whisper from across a continent, but they arrive, steady and disciplined. The same tones that once relayed images of volcanic moons and icy rings now carry information about the density of interstellar plasma and the direction of the magnetic field lines beyond the sun's grasp. It's not glamorous data, perhaps, but it's pure gold to the scientists who listen for it. And in that listening, there is something sacred, because listening is an act of hope. It says we believe there is still something to learn, still something worth hearing. Maybe that's the heart of the Voyager story. It never shouted. It never demanded attention. It just kept going. It taught us that wonder doesn't always arrive with a bang. Sometimes it comes pixel by pixel, bit by bit. A tiny dot on a screen that turns out to be a moon we never knew existed. The golden record, bolted to each spacecraft's side, was a final gift not to science, but to imagination. We didn't have to include it. There was no scientific requirement to send whale songs and greetings in Sumerian, but we did it anyway, because we hoped someone someday might find it. We hoped it would matter. And even if it never is found, it still mattered because the act of sending it, of choosing to say hello before anyone else did, revealed something essential about us. The stars have always been silent, but we spoke first. We sent music, laughter, the sound of footsteps, the crackle of thunder, the roar of rockets, and the hush of breath. We sent data and diagrams and the brainwaves of someone in love. We didn't send warnings, we didn't send threats. We sent wonder. Voyager's legacy isn't just about what it found, it's about what it inspired. New missions, new scientists, new dreams. It helped us realize that even our most distant machines can be storytellers, that even a spacecraft can carry meaning far beyond its mass, and that the farther we reach, the more we understand what it means to be home. One day soon, Voyager's power will finally run out. The signal will fade. The instruments will fall silent. No one will notice immediately. There will be no explosion, no dramatic farewell, just a long pause in a signal that never resumes. But even then, the spacecraft will not be lost. They will keep moving, slowly and steadily, among the stars, silent but not forgotten. And someone, perhaps us, perhaps not, might remember that we once built 2 small ships and sent them into the dark. Not for answers, but for the joy of the question. And maybe that's all the legacy we need. As the story of the Voyagers concludes, I want to ask you what I asked when we began. Are you still awake? Still drifting among the stars with me? Or have you already slipped off into sleep, Voyager's gentle signal carrying you toward dreams? Either way, thank you for joining me on this quiet journey. And if you've enjoyed this voyage through time and stars, please consider leaving a like and subscribing to the Midnight Scientists. It helps more dreamers find their way here and helps keep the signal going just a little longer. Till next time, rest well, stay curious, and remember, we spoke first.